Assalamu alaikum wa rahmatullahi wa barakatuh. This is the first video of Chapter 11, Part 1, Work and Power. At the end of this part, you're going to be able to determine the work done by a constant force, the work done by the constant force, which is weight, and define the average and instantaneous power. Mainly this part will be about the work done by a constant force in general. We generally use the term work to relate the activities in our daily life. In general terms, any physical or mental activity can be defined as work, like thinking, typing reports, reading, pushing a box, or kicking a ball. Yet the physical meaning of the term work is different from its everyday meaning. Let us first explain the physical meaning and then we will distinguish it from everyday meaning. In physics, however, work is used in a carefully defined manner. It is more accurate if you have a look on each one of these actions. The first one maybe. You may say the boy is dreaming. The second one, you may say that the man is gaming and not working. And even the boy, you may say that he is not reading, he is scanning pictures. But nothing will be said wrong about the boy who is pushing the box. And same for the child who is kicking the ball. So it is crystal clear that there is a force and a displacement. You can say that there is a difference in the usual linguistic definition of work and the definition of work in physics. So guess you got the difference in meaning now. Let's do a simple experiment together. For that, I need you to get an object like a book, a box, or a chair. So pause the video right here and go and get something to follow up with me. Are you ready now with what you get? I'm ready with mine. Otherwise, pause the video here and go and get your experimental material. When you hold this object like the box held by this man, are you doing work here by the upward force? Great. The force F doesn't exert a work since there is no displacement. You may feel the fatigue, but you are not doing a work. Second example. Try to push the object you had prepared as this man is pushing the chair by a force F along a distance d. Have you done any work now? The answer is yes, because there is a force involved and there is a displacement d. So you can notice the effect of the force when you are moving the object. We can say then that there should be both a force and a displacement for a work to be done. We conclude that a force exerted on a system does a work when it influences the movement of that system. There is no work without displacement. Besides, work is a method of energy transfer. When a force performs work, energy is transferred from a body to another or transformed from a form into another. We are going to study the work done by a constant force only. A constant force is a force that has a constant magnitude and constant direction. Consider these two examples. First, a lifting force is considered of constant magnitude along a distance AB and all the time directed upward, while pushing this toy car is also done by a force of constant magnitude and has only one direction. Now, can you give me an example of a force that always exists and is constant? It is the force of weight, which is of magnitude m times g. Both are constants and It is all the time directed vertically downward. This is another example. We are going to take a part of a motion done due to pulling a cart by an oblique force F. Yet we can see that the displacement is horizontal. The force in this example is still constant, since its direction and magnitude are constants. The force here makes an angle alpha with the horizontal, where the displacement occurs. Then we say here that the work is done along the horizontal and no work is done along the vertical. Then what is the expression of the work done by a constant force? By definition, the work done by a constant force while moving along the displacement AB vector is given as the dot product of F vector with AB vector, which is the magnitude of F times the magnitude of AB times cosine angle alpha. Here we say that W of F is the work done by the exerted force in joule. F is the magnitude of the force F in Newton. AB is the displacement in meters. Alpha is the angle F vector AB vector. Note that 1 joule is 1 Newton meter. Now let's ask this question. How can I prove from this expression that the work is done by the component of the force which is parallel to the displacement? I'm asking this question since we said before now that when applying an oblique force, the work is done along the horizontal and no work is done along the vertical. Consider the adjacent figure where the displacement AB is horizontal and the force is oblique. We can say that part of the force is along the horizontal, represented by F of x, and another part is along the vertical and represented by the y component Fy. Then we can write the expression of work F vector dot AB vector as F of xi vector plus Fyj vector, all of it dot product with AB I vector. Now if we expand it, it becomes Fxi dot ABI times Fyj dot ABI. We know that Fyj dot ABI vector is 0 since I dot j is 0. Keep in your mind that the angle between I with j is 90. So I vector dot j vector equals to I j cosine 90, which is 0. The last answer for the work done by the constant force is F of x dot AB, since I dot I is 1. And here notice that F of x is parallel to AB in this example. Then every time we want to use the expression of the work done by a constant force, we can use the component of force which is parallel to the displacement times the displacement. Till now we are representing examples along a rectilinear path. Would this expression vary if the path is curvilinear? Consider a constant force whose point of application moves from A to B along a curvilinear trajectory. Since the path is not rectilinear, we are going to divide it into small and consecutive displacements of delta L1, delta L2, delta L3, etc. Then it is considered nearly rectilinear with angle alpha with the direction of the force. Then the total work done by the force F from A to B is the sum of the work done by the force on each small displacement delta L. Thus, we can write it as delta work 1 plus delta work 2 plus etc., where delta work 1 is F vector dot delta L 1 vector, and delta work 2 is F vector delta L2 vector, and so on. Since F is a constant force, we're going to take it common. Then the work done by the constant force becomes F vector dot the sum of delta L1 plus delta L2 plus etc. By the property of the vectors, we can say that the sum of all successive delta Li is equal to AB. And here we conclude that the work done by a constant force is independent of the path followed by the object. Whatever the shape of the path followed between A to B, we're going to take the vector AB in our expression to find the work done by the constant force. Actually, the work is an algebraic quantity. It may be positive, negative, or null depending on the value of the angle alpha. How can we indicate this sign? If alpha is taken between 0 and pi over 2, this means that the work is positive because cosine alpha is positive. Here we say that the energy is transferred to the system and the force is motive. What if alpha is between pi over 2 and pi, where cosine alpha is negative? Then the work is negative. We say energy is transferred from the system, and the force here is resistive. If alpha is exactly pi over 2, the work is 0. Energy is neither transferred nor gained by the system, and the force here is perpendicular to the displacement and it does no work. Let's consider this example. Determine the nature of each of the following forces acting on the box while moving from point A to point B. The forces acting on the box are the weight, the friction, the tension, and the normal reaction of support. Let's start with the work done by the normal reaction of support. It is 0 since n is perpendicular to the displacement. What can you say about the work done by weight? It is 0. Now, the tension force, it is positive because the angle is 0 between T vector and AB vector. Finally, the work done by friction is negative and it is a resistive force. This is enough for today. Take notes and study well. Thanks for watching.